Okay, so the next problem that we're going to look at, this is on page 9 in our guided notes. We're going to be looking at problem number 414. I'm doing this one as a practice problem because you're going to see here when we look at our application problems, 415 is going to be a problem that you do. So in essence, we're getting a good setup for the problem that you're going to be doing for your application problems as well. And we'll talk about how it's going to be a little bit different. But we have the bracket BCD is hinged at C right here. So it's a pin connection at C. It's attached to a control cable at B. For the loading shown, determine the tension in the cable. Okay, that's right here. And the reaction at C. Okay, tension in the cable and the reaction at C. So our two supports here are the cable connected at B. Our body is, I'm going to call it like this L bracket. And then we have our point C where it is hinged. That's going to be a pin connection. And then two applied loads as we see there. So let's draw our free body diagram. I didn't leave much room here, so I'll probably have to add an extra sheet of paper, but we'll get started here. So first things first, we always have to put our convention. And then I'm going to draw our free body diagram. C, E, we have two applied loads. I always like to put those on first, 240 and 240. And this is newtons. Okay. And then as far as distances here, we've got 0.4 meters, 0.4 meters. Okay. And then we have, and I'm going to draw this as a dotted line. Okay. We've got our cable. And our cable is kind of more of an angle like this. And it's going to be on a line right here. Okay, so it told us that it's a cable. So we'll talk about how we're going to represent that in just a little bit. But we know that the height here from C out here is 0.18 meters. So that's the height from here to here. And then the distance, and I'm going to draw little dotted lines here out to where it would intersect. This distance from here to here is going to be 0.24 meters. Okay, so that'll help us with an angle. Okay, which we'll need. Let's talk about the supports now. So we've got our applied loads on, we have our points, we have our dimensions. Let's talk about our supports. At C here, this is a hinge or a pin connection. So if we go back to page 160, that is going to be like down here. So we're going to have an X and a Y reaction at C. So let's put those in. Okay, so this is going to be our CY. And I'm going to draw this as a CX. Now, I don't know the direction of CX, but I'm assuming a direction. I know I have to have an X and a Y component there because that's the directions that it constrains or supports in. So I'm just assuming a direction. So if you're asking me, why did you put it going to the right? Because I have to put an X in there and I'm putting it to right. Why did you put the Y up? I kind of saw there was two forces over here that are going down. I'm going to put my Y going up. Okay, because it has to support. So that's going to be my pin. Let's talk about B. B is a cable. Okay, if we go back to page 160, B is a cable. Now, a cable can only support when it is in tension, meaning it's going to be along the cable, pulling away from the body. If you recall, we identified that early on in our guided notes. Down at the bottom here, we were identifying reactions starting at the bottom of page 1 Continuing to page 2, you're going to notice that it says number 4, cables. We have one reaction along the line of the cable pulling away from the body, because that means that it's in tension. If a cable is collapsing or in compression, it's not supporting. So a cable always has to be in tension. So we're going to use that to determine that direction. So our body is the L. So our body is point B, if you would. Our cable then is going to be along that line. The reaction of that cable is going to be along that line, pulling away from the body. Okay. So this is going to be the reaction at C, the tension in the cable. We'll call this T. We'll just call it tension in the cable, T. Okay. Now it's at an angle, right? It's at an angle. So that means that we are going to need components. So we're going to need this angle, because that angle is going to be this angle, right? That angle is going to be that angle. So if we call this theta, for instance, we have the distances so we can figure that out. So we're going to have to say, okay, tangent of theta is going to be equal to the side opposite, 0.18 meters, divided by the side adjacent, 0.24 meters. Meters cancel, and we get our angle. So 0.18 divided by 0.24, I'm getting 36.87 degrees. Okay. If that's 36.87 degrees, so is this. Okay. So my TX right here, okay, it's going to be there. And then I'm going to have a TY going down. Okay. And now I'm going to have to resolve those into their components, right? So my step 2, I guess I'll put it here. It's going to be the components for that tension in that cable. Okay. So go ahead and do your components there. This is angle theta right there. Okay. Definitely not going to have enough space here to write all that work. I'll have to go on to another piece of paper. So we're going to put those X and Y components in terms of their hypotenuse, which is T. Okay. All right. I'm going to grab another piece of paper, and then we're going to continue on. So now that we have all of our forces identified, X and a Y component at our pin C, we have our tension in our cable, X and Y identified in terms of their hypotenuse, T, the tension in the cable, pulling away from B. And then we have our 2 applied loads identified. So now we're ready to solve for those reactions at the supports, okay? We need that tension in that cable and the X and Y at C. So to do that, I'm going to use my equations of equilibrium. So step 3 is going to be equations of equilibrium. Okay. First one, I always kind of tend to move this a little bit, sorry. I always tend to start with sum of the forces in the X equal to 0. So that's what I'm going to do here. So sum the forces in the X equal to 0. So I'm going to look, what do I have going on in the X direction? So I've got a negative TX, and I know that negative TX is 0.8 T. So I'm going to put it right away in terms of its hypotenuse. So negative 0.8 T. That's that one. And then I have a CX plus CX because it's pointing to the right. Those are the only two forces in the X direction. So that's what it is. So I'm going to just take that negative, put it on the other side. CX is equal to 0.8T. And I just kind of have to sit there, right? I should really put a line underneath there. I'll continue when I can. Then I'll do my next one. Do the sum of the forces in the Y equals 0. So now I'm going to look just in the Y direction, vertical forces. So I'm going to start here. I have a TY going down, negative 0.16T. So negative, I'm sorry, 0.6T, negative 0.6T. And then I've got a CY going up. So I'm going to have a positive CY. Then I've got a 240 going down, and that's newtons. And I've got another 240 going down, and that's newtons. Okay, and I'm at the end of my piece of paper. Luckily, I have to set that equal to 0. Make sure you do that. Remember, the sum of the forces are on the left-hand side of the equation. Then I have an equal sign, and I have to set it equal to 0. So now I'm going to combine these two, and I'm going to move them to the other side. So I'm going to have a negative 0.6T plus CY is equal to 480 newtons. Okay. Here again, I've got two unknowns, right? And unfortunately, in these two equations, I don't have the same two unknowns. This is not a concurrent force system. I've got a CX and a CY, but I do have a common T, but I can't use substitution method here. So now I've got one more equation of equilibrium, right? I've got my sum of my moments that I can sum around a point and set that equal to 0. So that's what I'm going to do next. So I'm going to sum. Actually, I'm going to leave a little bit of extra room. I'm going to leave room underneath here because I know I'm going to come back and fill some of those in. So I'm going to go down here. Sum the moments around. Now, the point that I'm going to choose to sum around, I'm going to go around C. Okay. You could go around B too, but I'm going to go around C for this one. Okay. And I'm going to set that equal to 0. And now I'm going to determine my moment equation. It's up here at the same time. So I'm going to put my finger on C. That means that I'm taking out CX and CY. And I'm going to start up here. And if I look at TY, it moves right through that point. So there is not going to be rotation. Okay. But TX does rotate. Okay. So that means that I'm going to have TX. That's going to be the magnitude of the force. So TX, and if I look here, TX is 0.8T. Okay, times perpendicular distance from C. Okay, this distance right here is 0.18 meters. 0.18 meters. Okay, and then the direction that it rotates, if I put my finger on C and I pull in the direction of TX, it's going to go counterclockwise. So positive out front, or because it's the first, it's an assumed positive. It's fine. Okay, so that's the only thing up here that is going to cause rotation. Now I'm going to move over to my 240. Yes, that's definitely going to rotate. So the first one is going to be 240 newtons times perpendicular distance from C here is 0.4 meters. And if we go back and we rotate in the direction, it's going to be going clockwise. So that's a negative out front. Okay. Then I've got one more force. Put my finger on C, pull in the direction of the 240. It's going to be 240 times perpendicular distance of 0.8 meters. And that also from C is going to rotate clockwise. So that means that it's going to be negative out front. Okay. Now that exhausts all of the forces causing rotation about C. So I set this equal to 0. Make sure you do that. This is the sum of the moments in the C, around C, sorry, is equal to 0. Okay. We have an equation. It has an equal sign, two signs. All right, so now what I can do is I can add and subtract. You'll notice that my only unknown here is T. That is good, right? So that means I'm going to solve for T. So go ahead and do the math to solve for T. And I'll do it here as well. So you should get 2,000 newtons for the tension in that cable. Just want a confirmation on that. I'm pretty confident. Yep. Awesome. Thank you, Tim. Great. Any questions? Got it, Tyler? Awesome. Thank you. So that means that as we look up here, the actual tension in this cable is 2,000. And it's along here. Even though we broke this into its X and Y components, remember, we put it in terms of the hypotenuse. So that tells us if we go and we size cable, we got to make sure that the cable that we get can hold at least 2,000 newtons. Okay. All right. That's one of the purposes, or one way that we would use this number. Okay. So we also need to determine what CX and CY are. So now that we know our T, we can go up here and we can solve for CX, and we can go over here and solve for CY. So go ahead and do that. And then I will solve on the side here as well, and we can compare. Should get 1,600 newtons for CX and 1,680 newtons for CY. Let me know if you also get those numbers.
I got those.
You got them, Nick. Thank you. Thank you. Thank you. All right. So are there any questions on the process here? So again, free body diagram first, nice and big. Make sure you've got all your labels here. Identify your supports, the types of supports, and then, use page 160 to help you determine how many forces you're going to need for that support. Break anything into components that you need to, and then we use our equations of equilibrium to solve. Okay. All right. I'm going to put that one to bed.